Have you ever wondered what's actually keeping the elevator you're standing in from just snapping? Or why the bridge you drive over every single day doesn't eventually collapse under the weight of 1,000 cars? Well, it all comes down to the physical limits of the materials we build our world with. Welcome to this explainer on the hidden physics of how solid materials stretch, compress, and ultimately hit their breaking point. Today, we're going to unpack exactly how physicists and engineers calculate these precise limits so that things don't fall apart.
Here is our logical progression for today. We're looking at 1. Stretching and compressing solids, 2. Understanding Hooke's law, 3. Energy and deformed materials, 4. Defining stress and strain, and finally, 5. The Young modulus. We're going to start with simple springs and build all the way up to the master equations that literally shape our modern world. Let's get to it.
Section 1. Stretching and compressing solids. First things first, we need to define the physical reality of the specific forces we apply to actually change an object's shape, because things don't just bend on their own.
To change the shape of an object, you have to apply forces in opposite directions. It's really that simple. If you've got two forces pulling away from each other, we call those tensile forces. Think of grabbing a thick rubber band and stretching it as far as it'll go from both ends. But if those forces are pushing inward towards each other, well, those are compressive forces. Imagine stopping on an empty soda can and crushing it flat. Both of these types of forces cause a very real physical deformation in the material.
Moving right along to Section 2, Understanding Hooke's law. Now, what actually happens when we apply these tensile forces to something elastic, like, say, a standard metal spring?
Take a close look at this graph, because this perfectly straight line from point 0 up to point A is absolutely crucial. That straight line proves that the extension of our spring is exactly proportional to the load we apply. It's perfectly predictable. If you double the physical force, you literally double the stretch. But notice point A right there. That is the limit of proportionality. The second you cross that specific point, the line starts to curve. The spring suddenly extends way more easily, meaning that beautiful proportional relationship is completely gone.
And that straight line we just looked at, that is Hooke's law in action. Mathematically, it's force equals K times X. That K right there is the spring constant, which we measure in newtons per meter. You can think of the spring constant as essentially a stiffness rating. A bigger K means you're going to need a lot more muscle to stretch that spring. But remember, and this is a massive trap people fall into, Hooke's law only works provided that limit of proportionality we just saw hasn't been exceeded.
So, what happens if we do push it too far? If we stretch that spring past its elastic limit, which is usually just a tiny bit beyond point A, we completely shift gears. We go from elastic deformation, where the spring snaps right back to its original length, straight into plastic deformation. Plastic deformation means the change is totally permanent. If you've ever yanked a coiled spring so hard that it just stayed stretched out and ruined forever, yep, you plastically deformed it. This raises a really interesting, essential question about the physics taking place right before that limit of proportionality is breached. Because you are actively applying force over a distance, which means you're doing physical work. Where exactly does all that energy go? That brings us perfectly to Section 3, Energy in Deformed Materials. Let's see how this physical work translates into stored energy inside the object itself. Honestly, this visual brilliantly illustrates the answer. The physical work done, the elastic potential energy, is quite literally the visual area of the triangle sitting right there under our Hooke's law graph. Since the force you apply increases steadily from 0 to a maximum force F, your average force is just half of F. When we multiply that average force by the extension X, we get the exact area of this specific triangle. It maps out perfectly. So the major takeaway here is that we actually have options. We can calculate the stored energy using either the force or the spring constant, as long as we haven't blindly crossed over into plastic deformation. We can use 1/2 force times extension, or if we substitute Hooke's law directly into the equation, we can use 1/2 K times X squared. They both get you the right answer.
All right, Section 4, Defining Stress and Strain. It is time to pivot away from simple little springs and talk about raw, structural materials. How do we measure something like a heavy-duty metal wire?
If we want to investigate how solid metal stretches, we have to collect incredibly precise measurements. We need specific instruments for this. First, we need the original length of the wire, measured directly with a meter rule. Then, we use a micrometer screw gauge to find the wire's tiny diameter so we can calculate its exact cross-sectional area.
And finally, because metals stretch such incredibly small, microscopic amounts, we have to use a vernier scale just to capture the precise extension.
Armed with those ultra-precise measurements, we can define our first massive concept, stress. We use the force and the cross-sectional area to calculate stress, which is measured in pascals, exactly like pressure. It's represented by the Greek letter sigma. This value essentially tells us how intensely the internal structure of the material is being pulled apart.
Next up, we calculate strain. Now, strain is merely a ratio of the extension to the original length. Because it's just a ratio of two lengths, it completely lacks units. No pascals, nothing. We use the Greek letter epsilon here. Strain is simply telling us the percentage or fraction by which the material has stretched compared to its original unloaded length.
Now, if we plot stress against strain, we get a graph that looks remarkably similar to our spring graph. Look at that straight line. This is amazing because it proves that Hooke's law universally applies to stretching solid metals too. The true beauty of this stress-strain graph is that it gives us general, universal information about the material itself, regardless of how thick or long the specific wire you're testing happens to be. Which brings us to the grand finale, Section 5, the Young modulus. This is the ultimate equation that brings every single thing we've learned today together. That simple ratio of stress to strain, it turns out it's a constant value that is entirely specific to each material. We call this the Young modulus, and we represent it with a capital E. Now, because strain doesn't have any units, the Young modulus simply takes the unit of stress, the Pascal. This right here is the ultimate number engineers look for to fundamentally understand a material's inherent elasticity. By vertically stacking our formulas for stress and strain, we can derive the master equation that engineers use every day. You just take stress, which is force over area, and divide it by strain, which is extension over length. Do a little algebraic flipping, and you get E equals force times length divided by area times extension, FL over AYX. It's an incredibly powerful tool.
Let's see how this builds in reality. Say we know the Young modulus of mild steel is 2.1 times 10 to the 11th power pascals. If a 250 Newton force is applied to a 1.5 meter wire with a 0.6 millimeter diameter, we just plug those numbers directly into our derived formula, and boom! We can predict the precise 6.3 millimeter stretch of this specific wire. It's basically structural fortune-telling.
Understanding this isn't just some abstract theory to memorize for a test. This is the fundamental math guaranteeing that the bridges we drive over and the buildings we inhabit never pass their breaking point. If the stress goes too high and the material shifts into plastic deformation, structures sag, they permanently warp, or they catastrophically fail. So the next time you step into an elevator, ask yourself, just how much faith are you putting in the Young modulus?